Welcome back. We will now continue our discussion about scientific truth. In this lecture, we continue to describe the rigorous measurement process, which will define the importance and dictate the format of significant figures in a scientific measurement. We started our discussion about measurements by describing the initial step, which was to choose an appropriate experimental method. In making this decision, we first thought about an instrument that would match the size of the measurement, and we also wanted to find a measurement that would have the appropriate accuracy and precision. Other factors considered in choosing a method included: how many samples do we want to analyze? How long will it take to do the measurement with this method? How much skill is required to use the method? How complex is the sample itself? And how many components are in the sample? The second step in the quantitative measurement is acquiring the sample, which is also known as sampling. Sampling can be the most difficult step and the source of greatest error in the measurement process. In chemistry, we usually collect a small amount of material from a much larger source, all the while hoping that our tiny sample is a good representation of the bulk material from which it was taken. For example, let's say the sample is the sand on a beach. From this perspective, the beach sand looks homogeneous. Now, a homogeneous mixture is uniform in composition throughout the sample. Another way to define homogeneity that is less subjective is to describe it as a mixture that has the same density at every point. And we'll talk about density later. Now, we can't go sampling the whole beach, but we can take a bit of the sand from the beach for study. The thing is, as we look closer and closer at the sand sample, we see that the beach sand is not homogeneous at all. It's a heterogeneous mixture, which is a mixture that is not uniform in composition and having points of varying density. This kind of system can be problematic, forcing us to take and measure several samples from the source, the beach, and hope that the sum of the samples represents the whole beach correctly. The third step involves the proper processing of the sample. This can be a very torturous part of the procedure. Let's look at an example. What if we wanted to measure the amount of caffeine in a particular chocolate bar? Usually, we can't just throw a candy bar into what could be a fragile $250,000 instrument and expect to get meaningful results. So, we take the chocolate and carefully process it to isolate the caffeine before putting it into the instrument. If we're really lucky, this processing step can be minimal. An example of a kind of measurement where we don't have to process and isolate everything would be a water sample in which we simply wanted to measure the pH, which is the acidity or basicity of the bulk water. In this case, we just simply insert a pH probe directly into the bulk sample. Now that's easy sampling. The fourth step is the elimination of interferences in the measurement. Many times, other chemicals that I'm not interested in measuring will be in the sample, and unfortunately may have similar physical properties to the chemical we're measuring. These other chemicals might interfere with our measurement, so we'll have to figure a way to compensate for this experimental anomaly. For example, when we weigh ourselves on a bathroom scale with our clothes on, or even at different times in the day, we'll probably get variability in our actual weight that we'll have to consider in trying to describe our weight. In my golfing analogy from the last lecture, there'll be wind and humidity effects that will alter the flight of the ball. In both examples, the interference can't be ignored and must be compensated for when we make the measurement and represent the truth. The fifth step is to calibrate our measuring devices and make measurements. To figure out the lengths of shots using various golf clubs, I had to spend hours at the driving range where the flag sticks were accurately placed at certain yardages, and I would shoot at them to make sure that my combinations of club and force were calibrated before I ever hit a golf shot on the actual golf course. If we really, really wanted to use our bathroom scale correctly, we would first weigh a bunch of materials that we knew the exact masses of, which we call controls or standards. From the measurements of these controls, we would produce a plot of the data. The actual known mass or weight of our controls we could plot on the y-axis versus the measured values read on our scale of those controls, which we plot on the x-axis. Now, it should be clear from the data here that the correlation is linear, which means that in this example, we can fit the data to a line equation. Doing what is called a linear regression fit of the data, the calibration equation was found to be y equals 0.9927, the slope, times x, plus 0.4363, the y-intercept. Now, when we take the reading on the scale, let's say the scale reads 147. We can correct the measurement using our graph, marking the measured value on the x-axis and then reading off the actual weight on the y-axis. Alternatively, we can just simply put the measured value of 147 into the linear equation as the x variable, do the math, and find the actual weight by calculating the y variable. Using both methods, we see that our 147 measured value on the scale correlates with an actual weight of 146.4 pounds. We now can be a bit more confident that the value we obtained from our calibrated scale represents our true weight and can be deemed accurate. Now, let's be real. How many of us would bother doing this with our bathroom scales? Most of the time, we just trust that the manufacturer did the calibration for us, don't we? But as a scientist who might be publishing the data for the world to see, and knowing that accurate data is critical in the building and testing of our precious hypotheses, we can't just hope the manufacturer got it right for us. It's critical that we know for sure that the machine is properly calibrated. Our scientific rep is on the line. Let's stop for a moment and consider what we've done. Look at all this effort that was required to do the measurement correctly. All these steps were our effort to minimize what we call systematic or determinate error. Now, this kind of error directly affects the accuracy of a measurement and is an error we should be able to identify and fix. Now, in our recent example of the bathroom balance, we could see the presence of the systematic error clearly, which we then fixed by calibrating the instrument using controls. Now, can we find all the systematic error? Well, we hope so, but we can't be 100% sure. But we have a much better chance of being accurate and finding that error, no matter the instrument, if we rigorously work through this multi-step measurement process. Okay, now we're not quite done yet. There's one step left in our measurement process, and it's the calculation of results. It's here where we try to quantify the pesky random error that's always present in scientific measurements. Now, I'll catch up with you in that lecture, okay? See ya.